In this lecture, we'll discuss time and space complexity, explaining both concepts and practical ways to find the time and space complexity of an algorithm. An algorithm is a measure of the amount of resources, primarily time and space. Space means memory space required to run it, expressed as a function of the input size, usually denoted as n. Time complexity measures the increase in execution time. Instead of measuring actual time required in executing each statement in the code, time complexity considers how many times each statement executes, whereas space complexity quantifies memory usage. Time complexity. The amount of computational time an algorithm takes to run, typically measured by counting the number of elementary operations it performs, example comparisons, arithmetic operation, assignments, and space complexity, the amount of memory an algorithm requires during execution, including space for input variables, temporary data structure, and the call stacks for recursive functions. For example, an array of a size n requires O of n space. Auxiliary space, this refers to the temporary or extra space used by an algorithm, excluding the input data. For instance, sorting algorithm like merge sort use O of n auxiliary space, while quick sort uses O of 1, mean constant. Asymptotic notation. Any software development life cycle, testing normally done worst case scenario. Here, big O notation, actually algorithmic complexity is commonly expressed using big O notation, like O of function fn, which provide an upper bound or worst case scenario for the algorithm growth rate as the input size n approaches infinity. Omega. Omega represents the best case scenario, providing a lower bound on runtime. But it is not preferable for any software development life cycle, because software sometimes may face worse condition. That's why during testing time it is required big O notation, not omega. Theta represents the average case scenario, bounding the runtime from above and below. Factor affecting time complexity. Actually, number of operations required, that is affect the time complexity. At space complexity, how much memory an algorithm requires for the size of its input. Growth rates of common time complexities. This one, constant time complexity remain constant, not depend on any input side. This one, exponential time complexity, O of 2 to the power n, rises rapidly and become infeasible for even small input size. Come to linear, O of n, quadratic, O of n square, and other complexity fall in the middle. This is very important. Logarithmic, O of log n, being particularly efficient for a bigger data set.